We often talk about two distinct tasks: policy evaluation and control. Policy evaluation is the task of determining the value function for a specific policy. Control is the task of finding a policy to obtain as much reward as possible. In other words, finding a policy which maximizes the value function. Control is the ultimate goal of reinforcement learning. But the task of policy evaluation is usually a necessary first step. It's hard to improve our policy if we don't have a way to assess how good it is. This week, we will look at a collection of algorithms called dynamic programming for solving both policy evaluation and control problems. By the end of this video, you will be able to understand the distinction between policy evaluation and control, and explain the setting in which dynamic programming can be applied, as well as its limitations. Dynamic programming algorithms use the Bellman equations to define iterative algorithms for both policy evaluation and control. Before diving into the details of this approach, let's take some time to clarify the two tasks. Imagine someone hands you a policy, and your job is to determine how good that policy is. Policy evaluation is the task of determining the state value function vpi for a particular policy pi. Recall that the value of a state under a policy pi is the expected return from that state if we act according to pi. The return is itself a discounted sum of future rewards. We have seen how the Bellman equation reduces the problem of finding vpi to a system of linear equations, one equation for each state. So, the problem of policy evaluation reduces to solving this system of linear equations. In principle, we could approach this task with a variety of methods from linear algebra. In practice, the iterative solution methods of dynamic programming are more suitable for general MDPs. Control is the task of improving a policy. Recall that a policy pi2 is considered as good as or better than pi1 if the value under pi2 is greater than or equal to the value under pi1 in every state. We say pi2 is strictly better than pi1 if pi2 is as good as or better than pi1 and there is at least one state where the value under pi2 is strictly greater than the value under pi1. The goal of the control task is to modify a policy to produce a new one which is strictly better. Moreover, we can try to improve the policy repeatedly to obtain a sequence of better and better policies. When this is no longer possible, it means there's no policy which is strictly better than the current policy. And so the current policy must be equal to an optimal policy, and we can consider the control task complete. Imagine we had access to the dynamics of the environment, P. This week is all about how we can use this knowledge to solve the tasks of policy evaluation and control. Even with access to these dynamics, we'll need careful thought and clever algorithms to compute value functions and optimal policies. For the next several videos, we will investigate a class of solution methods called dynamic programming for this purpose. Dynamic programming uses the various Bellman equations we've seen, along with knowledge of P, to work out value functions and optimal policies. Classical dynamic programming does not involve interaction with the environment at all. Instead, we use dynamic programming methods to compute value functions and optimal policies given a model of the MDP. Nonetheless, dynamic programming is very useful for understanding other reinforced learning algorithms. Most reinforced learning algorithms can be seen as an approximation to dynamic programming without the model. This connection is perhaps most striking in the temporal difference-based DYNA planning algorithm that we cover in Course 2. We will revisit these connections throughout this specialization. To summarize, policy evaluation is the task of determining the state value function vpi for a policy pi, control is the task of improving an existing policy, and dynamic programming techniques can be used to solve both of these tasks if we have access to the dynamics function P. See you next time, where we will learn how to use dynamic programming for policy evaluation.